Hi, my name is Kevin Greer. I work for the Resource Conservation District in Tehama County, and I run a program called the Mobile Irrigation Lab. Today we are out here in Colusa County doing an irrigation evaluation in an almond orchard on a drip irrigation system. So today we'll be out doing a typical mobile lab evaluation where we go through and we do a full audit of the system. And we start over at the pump by looking at the pressures and kind of how the pump's working, and then from there we'll do a full pressure test on this system. And once we have a nice pressure map and we know how the system is all pressurized, we'll do some flow tests to find out how the emitters are flowing, so we can do some DU calculations. Once we have all this information, we can take it back to the office and calculate the distribution uniformity of this system. We can measure the application rate, and while we're out here we'll also be looking for plugging, leaking, any kind of issues that may come up, and try to troubleshoot and figure out what those issues are and possible causes and then solutions to those issues.
And my name is Nancy Rice, and I'm here at Better Farms. It's just a 30-acre almond farm in Colusa County. I called the Mobile Irrigation Lab because I'm a beginner at managing irrigation, and I wanted to learn some things about my system, its efficiency, and how to manage it to save water.
So usually I start the evaluation by checking the pressure at the pump to find out how much pressure is being put into this system. So then when we make this whole pressure map out here, we can kind of see how much pressure has been lost between the filtration system and the irrigation system out here. And you have this pressure here at the pump, and you want to try and maintain that throughout the rest of the orchard. So we're going to start a pressure test now where we check a bunch of different pressures throughout this orchard. Right now we are on one of the first lines closest to the pump at the end of the line. So we want to know what the pressure is here on this closest line to the pump, at the end, at the inlet, and at the other end. So right now we're at the north end of this line. And to take a pressure test, we only need 3 simple tools. We need a pressure gauge with a pitot tube. We need a poker to poke a hole in the line. And we just need a goof plug to plug that hole. So I'm going to poke a hole in this line. Take my pressure gauge with the pitot tube and read the pressure, which this pressure right here is 18. And basically what I'm going to do is this a whole bunch more times throughout the orchard on some of these hose lines that are closest to the pump, intermediate, and furthest away from the pump. There's 2 submains on this system. So right now I'm on the southern submain at the end of the first line, and now we'll go down to the inlet of this line and check a pressure there, and continue down to the other end of the line after that. Now we are at the inlet of this first line where the pump comes into this submain that runs east to west. This is where the pressure on the system should be the highest. And what we have right here are a couple of manifolds regulating the pressure into this submain right here. So it's really important to check the pressure on these systems, because this is determining how much pressure is going into every single line that's connected to this submain right here, this buried PVC submain. So I have a pressure gauge with a special tool to be able to measure these, and I'll show you that in a minute. But right now we want to know what the pressure is right here and compare that to our last pressure we just collected at the end of the line. Okay, so we're at the manifold at the beginning of one of the submains, and both of the manifolds have pressure gauges on them. And one says 20 both say 20. So this is exactly what you want, is to make sure that all these manifolds, they have water that's coming into them and water that is going into the submain. And so the water that's going into the submain, you want to make sure that they're all the same. So you can adjust those at these manifolds and make sure that all the water getting put into these submains is the same across the whole orchard. However many of these you have. This system has 2 manifolds at each submain, and there's another submain. So this one has 4 of these manifolds. And right now, these are both reading exactly the same pressure, which is good and exactly what you want. And in just a little bit, we'll go check the other 2 and make sure they're the same as these. We've made a pressure map of this whole system, so I know where the high, medium, and low pressure spots are. So right now we are at the high pressure spot, and what we're going to do is do a flow test. And so we're going to do a catch cup test where we're going to place these cups underneath an emitter for 5 minutes, and we're going to do about 60 of these throughout the whole flow test area. I'm going to do about 12 in this high pressure spot right here, and 5 minutes in each cup, and then we'll measure the water and we'll see how uniform the water is in this one location where the pressure is the highest. To perform a flow test, you just need some cups and a timer, and if we want 5 minutes in each one of these cups, we're just going to start at 0, and then every 10 seconds I'm going to place this cup underneath the emitter. These drip lines are nice because you can pull them off of this sloped hill and pull them out where it's flat, and get your cups lined up where the emitters are and just slide them right under for every 10 seconds. So now we've just collected 12 flow rates from 12 emitters, all in this one location with this uniform area of pressure, which was the highest pressure in the system. So now we're just going to go through and measure each one of those cups and write down the number. These are collected in milliliters. Typically what I do is I collect all these, chart them all down, take them back to the office and convert them from milliliters into gallons per hour and into inches per hour, and an application rate based on the spacing, number of emitters per plant, and the amount of time that we collect water. So we just collected flow rates from 12 emitters, and we had a variation in there of 30 milliliters. So I believe 147 was our low, 177 was our high. So that's a 30 milliliter difference. If we multiplied that out to an hour, 30 milliliters in an hour, it would be 360 milliliters. Our grower here runs this system for about 48 hours a week. So if we multiplied that out, it's a little over 17,000 milliliters. You divide 17,000 milliliters by gallons, it comes out to about 4.5 gallons. It's a really long run time, is running these for 50 hours a week, and all these emitters we just checked only vary by a little over 4 gallons. Is one of the real strengths to having a drip irrigation system. Now what we can do, since we know where the low pressure spots are, is go to a low pressure location and see how much difference there is between the flow rates of these emitters here, where we know these emitters are putting on similar quantities of water, is to find out if that other location where pressures are different, if they're putting on a similar quantity as right here. And then we can figure out what the uniformity of this system is. We just completed the last flow rate test, and this is in the low pressure spot. The pressure here was about 5 psi lower than the high pressure spot, and we found slightly lower flow rates here, as we'd expect. So basically what I do now is take these calculations back to the office and calculate what the distribution uniformity of this system is. And the point of the distribution uniformity is to understand flow rates in these low pressure points and the high pressure points, and to find out the variation in those areas so we can make recommendations for improvements if necessary. Distribution uniformity numbers are typically expressed in percent, so 80% 90%, 85%, 90%. Typically these micro drip systems are designed to be incredibly efficient, so we can find uniformity ratings in the 95% range, but they are designed to be 90% and above. So the reason for making those calculations is being able to determine how efficiently is this system running, and is it running as efficiently as it could be. This is an area where the drip hose lines are connected to the submain, commonly known as inlet tees. And there are a couple of things to check here that are really important. One is this little valve right here that turns on and off the hose line. And oftentimes I'll see these where they're not fully open, and that can drop the pressure quite a bit if they're not fully open. So just checking them and making sure that the valve is completely open is really important. Another thing is to be able to close them and open your inlet tee and check for plugging, especially if there are screens inside. This one and this system does not have screens, so typically that's what's recommended. Every area is a little bit different, but those screens can be a high maintenance problem. So just checking these occasionally, making sure they're clear, running these and flushing them out doesn't hurt. They're pretty easy. Just turn off the valve, open it up, look at it, flush it out, and then turn it back on. So one other important maintenance tip would be to regularly check and flush hose lines. It can be a lot of work with how many hoses there are and different submains, so flushing every hose line takes a lot of work. But one tip would be to just check the lines regularly at the ends of submains. So we're out here at one of the last rows at the end of the submain, and this tends to be where all the debris ends up and goes to. So regularly checking these areas can tell you a lot about what's going on in the rest of your system. So water tends to be clean out here on the edge of the rows, on the edge of the orchard or the system. Then checking the other lines probably isn't necessary. So we're just going to open this up and just kind of see how long it takes for us to get clear water out of this system, and also kind of look to see what kind of debris we're finding in here. This system is running off of an irrigation district using surface water, so we expect to see some silt and sediment. This was all really fine silt that was in here, and it took about 10 or 15 seconds to clear out. But just checking those on a regular basis, getting that debris out of the hose line is really important. So the system may need to have some of its other hose lines checked, just because it took 15 seconds or so to get all of that debris out of this line. And then following up in the next irrigation or 2 or 3 to see how quickly it's reaccumulating in here. It may have been a while since this system has been flushed, or this hose line has been flushed. So just kind of getting an idea of how frequently to do it on how quickly sediment builds up in the lines is really important.